In today's lesson, we're going to work on projectile motion problems that will help us to calculate the maximum height and the range of a projectile. So let's begin with this problem. A ball rolls off a cliff at 15 meters per second and hits the ground 6 seconds later. What is the height of the cliff, and how far from the base of the cliff will the ball hit the ground? Now, for each of these problems, I recommend that you pause the video, try it yourself, and see if you can get the right answer, and then play it when you want to check your answer. Now, the first thing we need to do is draw a picture. So here we have a ball. It's rolling horizontally off a cliff, so it's going to follow this particular trajectory. Now, we know the initial speed of the ball. It's 15 meters per second, and we know the time it takes to hit the ground. It's 6 seconds later. How can we determine the height of the cliff? The height of the cliff is going to be 1/2 gt squared for this particular trajectory. You could find this formula in the formula sheet that I have below in the description section of this video. I recommend printing that formula because it's going to be very helpful for the problems to come in this video. So the height is going to be 1/2, g is going to be 9.8, and t is 6. 6 squared is 36, half of that is 18. 18 times 9.8 is 176.4 meters. So that is the height of the cliff. Now for part B, we need to determine how far from the base of the cliff will the ball hit the ground. In other words, we're calculating the range. So we already know the height. What is the range? The range is equal to Vxt. And for this problem, initially the ball is moving in a horizontal direction, in the x direction. So for this particular trajectory, V initial is equal to Vx, and Vx doesn't change. It's constant throughout this trajectory. Vx is also equal to V initial cosine theta. However, when you're moving in a horizontal direction, the angle is 0, and cosine of 0 degrees is 1. So this becomes just V initial t. So it's 15 meters per second times 6 seconds, which will give you 90 meters. So that's the range for this particular projectile. You simply multiply the initial velocity by the time, and you'll get the answer. Now, let's move on to the next question. A ball is kicked from the ground at 40 meters per second at an angle of 30 degrees above the horizontal. So what is the maximum height of the ball? So let's begin by drawing a picture. So here's the ball. It's kicked from the ground. It's going to go up, and then it's going to go down. So we know the angle, it's 30 degrees, and we know the initial velocity of the ball. It's 40 meters per second. How can we determine the maximum height with this information? Once again, if you've printed the formula sheet that I have in the description section below, you can find this equation. The maximum height is going to be V initial squared sine squared theta over 2g. So V initial is 40. This is going to be 40 squared, and then sine of 30, and then we need to square that, divided by 2 times 9.8. 2 times 9.8 is 19.6. So I'm just going to put 19.6 on the bottom. $40 squared is 1600. Sine 30 is a half, so 1600 times a half is 800, times another sine 30. That's going to take it to 400, divided by 19.6. You should get 20.4 meters for the maximum height attained by the projectile. So this is going to give you this answer. That's 20.4 meters. Now, part B, determine the range of the projectile. So the range is going to be this horizontal distance from where it lifted off from the ground to where it lands. Now, you could use the previous formula that we had in the other problem. Range is equal to V initial cosine theta t. The only problem is we don't know the time it takes to go from point A to point C. So we don't want to use this equation because we need to solve for t in order to use it. There is, however, another equation that we could use in the formula sheet down below. And here it is. The range is equal to V initial squared times sine 2 theta over G. So V initial is 40. Theta is 30, so 2 theta is 60. And G is 9.8. 40 squared is 1600 times sine of 60. That's 1385.6. Divide that by 9.8. You're going to get 141.4 meters. So that's the range of the projectile for this problem. Now let's move on to this one. A ball is kicked from the top of a 300-meter building at an angle of 40 degrees above the horizontal with an initial speed of 50. Let's draw a picture. So here's the ball. It's going to go up and then it's going to go down. So it's launched at a 40-degree angle. The initial speed is 50 meters per second. Let's call this point A, the top, point B, and point C. Now we know the height of the building is 300 meters. So you can call that H or Y initial. Part A, determine the maximum height attained by the ball relative to the ground. In my formula sheet down below, this is the maximum height for this trajectory. Lowercase h would represent the height of the building, which is the same as Y initial. So the formula that you need to calculate the maximum height attained for this specific trajectory, here it is. It's Y initial, or the height of the building, plus V initial squared sine squared theta over 2g. That's how you can calculate the maximum height. So it's going to be 300 plus V initial squared, so 50 squared, and then sine 40 degrees, but we got to square that. And 2 times g, 2 times 9.8 is 19.6. So 50 squared is 2500. If you multiply that by sine 40 2 times, that'll give you about 1032.9. Divide that by 19.6, you get 52.7. Add 300 to that. That will give you the maximum height, which is 352 approximately 0.7 meters. So that's the answer to the first part of the problem. Again, you could find that formula in the formula sheet. Now, part B, how long would it take the ball to hit the ground? So we want to find the time it takes to go from point A to point C. Now, there are two formulas that in the formula sheet that will help you to find this. Here's the first one. It's V sine theta over G plus the square root of 2 times the maximum height attained divided by G. So this formula is useful if you already know the maximum height. I'll show you another formula that you can use if you don't know the maximum height. So this is V initial, by the way. V initial is 50 times sine theta. V initial sine theta is equivalent to Vy, or Vy initial. So it's 50 sine theta over 9.8 plus the square root of 2 times 352.7 over 9.8. So when you plug that in, the time is going to be 11.7636 seconds. So that's how long it's going to take the ball to hit the ground for this particular trajectory. Okay, let's confirm that answer with another formula. So you can also get the time using this. It's v sine theta plus v initial squared sine squared theta, which is basically vy initial squared, plus 2g y initial. Anytime you see v initial sine theta, that's vy initial. This equation comes from the quadratic formula. The quadratic formula gives you two answers, but this simplifies it where it gives you this answer and not the answer that's over here. So v initial is going to be 50 times sine 40. And then on the inside it's going to be 50 squared times sine 40 squared plus 2 times 9.8, and then the initial height, y initial, which is 300. And that's all within the square root. All of this is divided by 9.8. Go ahead and plug that into your calculator. When you do, you should get the same answer, 11.7636. So those are the two ways in which you can calculate the time it takes to hit the ground. As you could see, you don't need the maximum height. What you do need is the initial speed, the launch angle, and the height of the cliff. With those three things, you can find the time it takes to hit the ground. The other formula, you don't need the height of the cliff, but you do need the maximum height attained from the ground. So now that we have that, let's move on to part C. Calculate the range of the ball. So we need to calculate this distance here, the horizontal distance traveled before it hits the ground. So for this one, we could just use range is equal to v initial cosine theta t. We know v initial, it's 50 meters per second. We got the launch angle, it's 40 degrees, and we now have the time it takes to go from point A to point C. That's 11.7636 seconds. Let's go ahead and plug this in. 50 cosine 40, that'll give us Vx, which is 38.3, times 11.7636. So the range is 450.57 meters. So that's how you could determine the range for this type of trajectory. Now, part D, what is the final velocity of the ball just before it hits the ground? So we're going to do this two ways. If you have the formula sheet, you can go straight to this formula, which will basically be a straight shot to the answer. The final velocity is v initial squared minus 2gt v initial sine theta, where theta is the initial angle, plus gt squared. And we'll confirm this answer using some other formulas. All right, let's see if we can fit everything in. V initial is 50 minus 2 times 9.8, and the time is 11.7636. V initial is 50 times sine of the angle is 40, and then plus gt squared. I'm just going to put that here, plus 9.8 times 11.7636. Now, of course, this is still under the square root. So don't put this outside the square root. This is still inside the square root. I just ran out of space. So if you plug this in, square root 50 squared minus 2 times 9.8 times 11.7636 times 50 times sine 40 plus parentheses 9.8 times 11.7636 close parentheses squared, and that's all inside the square root. So this should give you a final velocity, well, the final speed of 91.542 meters per second. The reason why I say this is the final speed is because we don't have the direction of this vector. We need to find it. Our goal is to find the velocity. So we need the magnitude, which we already have now, and we need the direction, the angle. So there's multiple ways in which we can get the angle, but right now, instead of using arctan, arc cosine is going to be easier because we don't know Vy. So for this particular problem, given what we already have, another way to find the angle is to use arc cosine of Vx over Vf, adjacent over hypotenuse. Now Vx is V initial cosine theta, where theta is the initial angle, and this is V final. So it's easy to use this formula because we already have everything we need. V initial is 50, and then times cosine 40 over V final, which we now have 91.542. So if you plug it in correctly, you should get this angle. This is the reference angle, by the way, the angle within the triangle. It's 65.265. I'm going to round that to 3. So 65.3 degrees. Now let's talk about what it means. So here's the vector. That's Vf, as you can see here. It's going in the quadrant 4 direction. This is Vx, this is Vy, and here's the angle theta. So this is the 65.3 degrees. It represents this angle here. So it's 65.3 degrees below the x-axis. If you need to find the angle measured counterclockwise from the positive x-axis instead of below the x-axis, you could do 360 minus 65.3 degrees. So it's also 294.7 degrees measured counterclockwise from the positive x-axis. So you have multiple ways in which to describe the angle. But I'm just going to say 65.3 degrees below the x-axis. So we have the magnitude and the direction below the x-axis. Now let's confirm our answer. So Vx, we know it's V initial cosine theta. So that's 50 cosine 40 So Vx is 38.3 meters per second. Vy, it's, perhaps you've seen this equation. V final is equal to V initial plus AT. So you could say Vy final is equal to Vy initial. Now A is going to be negative 9.8, but if you put minus G, G is positive 9.8. The effect is overall this should be negative because gravity brings things down. Now Vy initial is basically V initial sine theta, and then we need to minus GT because that velocity component is under gravitational acceleration. So every second the velocity in the y direction will decreased by 9.8. So that's why we have negative GT. So this is going to be 50 sine 40 degrees minus 9.8 over the times the total time of 11.7636. So 50 sine 40, that's 32.13 minus 9.8 times 11.7636. We're going to get a negative answer. And the reason for this is because it's going down. So this is negative 83.14 meters per second. So let's draw a picture. If we focus on this vector here, it's still moving to the right. That's Vx. So that's why Vx is positive. It's going down. Vy, it's negative. And V final is going in this general direction. Now notice that this forms a right triangle. So to find V final, we could use the Pythagorean theorem. C is equal to the square root of a squared plus b squared. So V final is equal to the square root of Vx squared plus Vy squared. So Vx squared, that's 38.3. Vy, once we square it, it will be positive, so 83.14 squared. When you plug this in, it will confirm this answer. Now I got 91.5796. So that's going to round to 91.6 instead of 91.5. But keep in mind, I'm using rounding answers here. So that's why it's a little bit off from what we have here. This is more accurate because we plugged everything in directly. We didn't use any intermediate answers. So this answer is more correct. But nevertheless, 91.6 or 91.58 is still close to 91.54. So as you can see, we still get about the same answer. Now let's get the angle theta. So if you know Vx and Vy, you could use the arctangent formula. Before we had Vy, we had Vx and V final. So we could use arc cosine instead of arctangent. But for this one, it's going to be arctangent Vy over Vx. Now for Vy, plug in positive 83.14. Don't worry about the negative sign. Otherwise, you'll get a different answer. So arctangent 83.14 divided by 38.3 will give us the same answer, 65.3 degrees. So all the formulas that we've used in number 3, you can see they have been confirmed. And again, if you want to find those formulas that will lead you to the answer directly, feel free to check out the links in the description section below. I kind of slurred my words a bit, but you'll find that formula sheet in the description section below for those of you who want to print it out. I think it's going to be very helpful when you're solving difficult projectile motion problems. It took a while to create that formula sheet, but I know some of you have been asking for it, so I decided to put it on my Patreon page. And it's free to download once you join that Patreon account. Thanks again for watching.